Well, okay, the bar at the bottom there is still showing, but I think we're just going to roll with it. So good morning, everybody. I'm Richard Otis. As our moderator said, I'm a PhD candidate at Penn State. I'm a material scientist, and I work extensively with Python. Zikwe Liu is a professor at Penn State. He's my advisor. And this work is sponsored under a NASA Space Technology Research Fellowship. So I wanted to talk a little bit about what the CALPHAD method is, because the package is named PyCalphad, so you should probably know what CALPHAD is. And CALPHAD is a very contrived acronym for the calculation of phase diagrams. But it's more than just the calculation of phase diagrams. It has to do with describing the thermodynamic properties of any material by constructing models for the energies of phases that are in the system. But not just the stable phases that are in the system, but also possible phases that are in the system. So what we usually refer to them as metastable phases. So we construct parametrized models for the phases that exist in those systems. And then once we have those models, yes, we can calculate the phase diagram, but we can also compute all sorts of thermodynamic properties of, in the case of my research, alloy systems. And we can do that by considering both equilibrium and non-equilibrium properties of those materials. And here I've listed a little bit about the mathematical model behind these, as well as a depiction of the energy surface of a three-component material and how it relates to mapping on the phase diagram here. And this method, this CALPHAD method, has been around essentially since we've had ubiquitous computing. It was pioneered by Larry Kaufman in the 70s, and it's essentially been going on and continuing at pace ever since then. But so the CALPHAD community right now is facing a lot of challenges, and I would say probably the most significant challenges have to do with data. And number one challenge is data fragmentation. And that has to do with this workflow here that I've depicted on the right-hand side here. And it has to do with the problem that we need experimental data for our models. So our models are fit to experimental data or from first principles data computed from quantum mechanics. They exist in disparate sources, disparate formats all over the literature. So that means anytime you want to develop one of these models, you have to do exhaustive searches. There's no clearinghouse for this data. There's no, as I mentioned the second point, there's no standards for the data, so you don't know exactly what you're going to get. But moreover, once you've gathered the data, you have to go through this process to actually get it into a format that you can use to fit your models. And then also you iteratively try to figure out what are the best parameters for the model. It's not all automated. There is some subject matter expertise that has to go into what reasonable parameters are. And while you do that, you see these gray boxes. They depict the fact that you lose history, you lose metadata all through this entire process. And then finally, you publish these parameters. A lot of times as a text table. Sometimes, if you're lucky, they publish it in a format called TDB, which you can download digitally. And then once again, it's fragmented because it goes into disparate sources. And so this is how CALPHAD, this is how the computational thermodynamics community has disseminated its information now for the past several decades without really a lack of good workflow tools. Fourth is uncertainty quantification. I didn't mention anything at all about putting error bars on any of the data points or any of the models here that I've mentioned. That's a significant concern. And all of this links down to this question of reproducibility of your models. And reproducibility is important not just from a scientific standpoint, right? Like in principle, every scientific analysis, especially computational ones because it's so easy, ought to be, as close to perfectly reproducible as possible. But there's also a practical reason why we care about this in the CALPHAD community, and it has to do with this problem, the problem of maintaining CALPHAD databases. So here I'm depicting a hypothetical 6-component system, A, B, C, D, E, F. You could imagine this as elements in the periodic table, so like nickel, iron, cobalt, chromium, and so on. And so the way CALPHAD databases are built up is they're built starting from the pure elements. So in our community, we have an agreed upon standard for all the pure elements, and we fit the binary system, so we add in parameters that describe binary interactions between the components, and then finally ternaries to describe ternary interactions between components. Thankfully, nature cut us a break. We don't have to go up to higher order. We can do linear combinations of the ternaries, and that basically has you covered for metallurgy. So I would say in the community right now, most of the binary systems are done. There's pretty good descriptions. Ternary is sparse, but a lot of the important ternaries are done. But the challenge here is, what happens if you decide to change an important binary? Say, if you're a nickel-based superalloy person, aluminum-nickel is one of the most important binary systems. Let's say you want to make a change to aluminum-nickel. This also isn't hypothetical. This is something we're discussing in the community. We want to make a change to aluminum-nickel. That means every system that contains aluminum-nickel up above, and you have to consider we go to higher order, 7, 8, 9, 10 component systems, you have to modify all of the upstream systems. Or what if you want to make a change to one of the pure elements? So this is something that we're talking about right now. We've recently, in the community, developed new stabilities for all the pure elements. They're to get the low temperature, like going down to 0 Kelvin, get those properties more correct. But that committee actually hasn't released their results. And the reason is because they're afraid of fragmenting the community even further by basically having people fit to 2 different standards. And so this is an example where our data management practices are actually holding our field back because we can't move on to the next evolution because we have all this legacy data that we have to manage. And so this is a significant enough problem. My advisor co-wrote a paper with some scientists from NIST talking about this problem and about how we can further improve our infrastructure and what are the needs for our infrastructure and how do we make it better. And the key takeaway I think we took from this was we wanted to be able to make PyCalphad, this tool I'm talking about today, a key part of that in terms of building on top of new, more open infrastructure that also can leverage all the great technologies that have been developed across the scientific Python community. So our goal for PyCalphad is we're developing these open source, permissively open source licensed implementations of all the core routines for CALPHAD, including phase diagrams, property diagrams, also solving the inverse problem. So if I know kind of what my phase diagram looks like and I know something about the thermodynamic properties of a material, can I fit a model, right? So a lot of this is I have a model, I want to calculate the diagram, but we also want to be able to go the other way. And then this is specifically dealing with multi-component and multi-phase alloy systems. So I'm a metallurgist, so I mainly focus on alloys, though there's nothing that precludes you from being able to apply something like this to a ceramic system or even a polymeric system. So the key steps when you want to compute a phase diagram are you have to sample the energy, in this case the Gibbs energy in composition space. You need to then you need to determine the phase relations at all those compositions. Which is equivalent to minimizing the energy under the constraints. And then the third step is you draw the diagram. So the first challenge you run into when you want to sample composition space is compositions are like fractional quantities, which means they have to add up to 1. And it can be kind of tricky when you want to figure out a reliable and consistent way to sample a space that's constrained. And so you can see this example here on the left-hand side. So imagine we have a 3-component system. So y1, y2, and y3 is equal to 1 minus the sum of y1 and y2, right? So that means that this white triangle here, which is called the Gibbs simplex, is the feasible region. Whereas if you go out here, stuff starts summing up to be more than 1, which means you get negative fractions, so it's not feasible. So we want to sample this triangle here uniformly. And we also need to be able to do that in an arbitrary number of dimensions. So the solution that I developed was to use something called a Halton sequence, which I'll describe a little bit more. It's really nice because it's like a uniform random sequence, except it's deterministic. It's the same every time. But mathematicians have proven that if you add enough points, the Halton sequence will behave uniformly. Thank you. And so it has this uniform random sample. It's fully deterministic, and it uses prime numbers. You can read more about it on Wikipedia. And so we have this convex hull method, which is what we use in PyCalphad 1. I just finished on the plane a new version, PyCalphad 2, which improves over a quick hull. Because of the nature of the problem, we can get slightly better performance. And it's the idea that we map this triangulation of the surface, and it maps directly to the phase diagram. And so PyCalphad had its first public release in April. It's right now about 5,000, 6,000 lines of code. There's been 800 commits, and it works well in the notebook. That's how I like to use it. And you can find it on GitHub. The core architecture uses PyParsing to read in TDB files. We have a plan to eventually build a REST API. It feeds into a model object using SciPy, and then using Lambdify, it's converted to more efficient representation. And then we use NumPy and also a package called X-Ray, which is awesome, by the way. I don't know if you guys are familiar with X-Ray or not, but it's a tool for labeling the axes of NumPy arrays, so you can do operations with labels, which is really nice. And then finally, you get plotting in the user output. And so if I want to fit data to a model, then what we can do is, so this is a work in progress, and if you're interested, you can track the fitting branch on my Git repo. So if you want to do the fitting, which is kind of the inverse problem, we have this idea we use this fit model function. And so the idea is you take the result from fit model, you plug it into this keyword argument, you get a dictionary of models. Those models then plug into another keyword argument in the plot function. And so what do you get is you get these parameter. So you get on the left-hand side, you have some initial guessing that happens. And then on the right-hand side, you get the fit that you get after you perform it. And in both cases, we get the fitted parameters. Soon, you won't have to guess. I'm working on this so that it does all the guessing for you, and then you can really start automating this process. Also, you get uncertainty quantification. These uncertainties are actually terrible because of the nature of the data set that I used, but it goes to show that you can actually start taking your experimental data and get uncertainties. And all these, the correlations and the uncertainties were computed with the LMFit library. Also, I just want to do a quick plug for like just general computer science. Vectorization is really important. I started out writing the code unvectorized, but then when I moved to a vectorized algorithm, I saw a jump of an order of magnitude improvement in performance. So it's definitely a good idea when you're thinking about writing scientific code and you have a performance critical part, you should look and see if this is something that you can do to improve your code. So finally, on the roadmap, I'm developing a new unified equilibrium routine, which will handle all the plotting and point equilibrium and mapping and everything. That ought to get done in the next 2 weeks. I'm very excited about that. The improved residual functions are on track for 0.3, which is not this coming release, but the next release. So probably before the year's out. Also for REST-based interfaces, and then of course ever more the bug fixes and performance improvements. So thank you. I really appreciate your attention. I also just want to do a quick plug. My advisor startup is hiring. If you're interested in this kind of stuff and know MongoDB or REST, you should reach out to me. Thank you.